Let's do this one more time. Same boundary, same region. Oh, by the way, just make sure you get your bearings right. This is X, this is Y over here. So the original boundary was this one. Here's the square root of X, here's Y equals X squared, but we're gonna revolve it around the line Y equals 2 this time instead. Let's see what happens. Again, I hope you can see, even from my rough drawing there, we are again gonna have washers. So we're gonna sum stuff up. What stuff? Yes, exactly. That's what you need to be thinking about, is what stuff are we summing up to get the volume of this overall object formed. When that region is revolved around the line Y equals 2, we should be thinking about washers. And so, take the whole solid cylinder's volume, subtract the volume of the whole, stamp out that centerpiece, and you'll get the volume of a particular washer. If we sum them all up, and again, notice here I factored out the H, and again, H is that little infinitesimal change in X that you've seen in the other videos. But what I want to focus on in this video is, how do you figure out those radii there? So come over here with me, and let's think. This is not a, oh, I just always do it this way, or I always do it that way. No, you always think. That's what you do. Let's talk about the big R. Big R is from here to here. That's the overall radius of that washer. Now, here's a question for you. How far is it from here to here? I hope you'll agree that that distance is a grand total of 2 units. How far is it from here to here? I hope you see that as X changes, that output, that vertical length there, outputs depending on the function f of x. And so this whole distance is 2, minus this whole distance is f of x, gives me the radius that I desire. Yeah, this time, because of the way we're revolving it, we have to think about that overall distance of 2, but then we have to take away that little short piece down there at the bottom, the f of x. And that f of x varies depending on x. Like if we were in here, f of x would be bigger. If we were back here, f of x would be smaller. But still, we're going to take the 2 and then subtract f of x. Take 2, subtract f of x. So your big R, sorry, I went too far. Your big R right here is the 2 units minus the f of x gives you the remaining radius. So what goes here for big R is 2 minus f of x. Now, what about the radius of that hole? We're going to stamp out the, where there is no material, you could say, this radius right here. So again, I'll ask you, how far is it from here to here? 2 units. How far is it from here to here? Notice now we're talking about not f of x, but we're going from some input value of x. We're coming up to this function, this concave down function, which was the square root of x function. So this distance is the square root of x. So 2 minus g of x would give you the radius of the hole. Can I just pause here? I would encourage you so much to stop this video, get out a piece of paper and a pencil, sketch this picture. Maybe you can make it better than I can. If you have a nice picture of it, scan the PDF and upload it and share it with us on Canvas. But here's the point. You need to stop and see, why am I measuring this as 2? Why am I measuring this as f of x? And why am I subtracting them to get the remaining radius distance? Or why am I taking 2 and subtracting g of x to get that inner radius, that lower radius for the whole, the lowercase r radius for the whole? Why am I doing that? I think it's important for you to actually draw it out and start thinking through it for yourself. But once we get it set up, then we can say the volume of this object is going to be that integral again from 0 to 1. We can factor out the common factor of pi, and we can say 2 minus f of x. Ooh, but what is f of x? F of x was x squared 2 minus g of x, the square root of x. Whoa. And then all of that got multiplied by dx. That would be the setup for the integral that would give the volume of this particular object revolved around y equals 2. Now again, I'm going to emphasize that it's the setup of the integral that humans really need to engage in. Once the integral is set up, technology is more than happy, if technology can be happy, to do the computations for you. So go ahead and compute away and report the volume of this object.